Okay, at least this works for me. So I am a retired antenna engineer doing my PhD, and I have developed a new GPR antenna type. I call it gopher antenna, and this is part of the study. Side-looking antennas or side-looking beams are quite common in remote sensing. So therefore, I thought, can it be done in a ground-coupled GPR radar? So here in this slide set, I suggest a practical solution, and I'll also demonstrate some use cases. So GPR tilting, is it useful? I met one archaeologist, and he said that medieval urban areas who have demolition layers, so one cannot see a GPR through a demolition layer. But this side-looking radar could see something from the side. So how to produce a slanted beam? Gopher antenna has narrow beam. It's a requirement for tilting. And what I'm using is a loosely rolled neoprene sheet. It will compress between the antenna and the ground. And the electrical properties of the neoprene are similar to the common properties in the ground. So gopher antenna generates a narrow beam. I made simulations with the typical commercial antennas, some sort of dipole, and it has a quite wide beam. And the gopher antenna has a much narrower beam. So tilting the antenna box tilts the beam. Here are some more simulations. The simulation area was something like this. It's quite cubic, but resulting electromagnetic picture was something like this. So it showed that tilting the antenna box 60 degrees upwards produces a beam tilted about 45 degrees from the vertical. So after simulation, I rotated the result so that the ground level is horizontal. And here is the tilted antenna, and here is the neoprene prism. So here I can show how it happens in practice. So this box here contains the antenna and the GPR electronics. This tablet collects the data, and here in this plastic bag is the neoprene roll. And for the target, here is the foundation, concrete, and gravel. I can show it once more how I did it. And it's the same as the text. So currently it's 500 megahertz central frequency. And the results, the resulting profile was a bit surprise. Something like this. But after I started analyzing it, I think it's all right. So this red line is for the bedrock here, and this blue line is for the wall. So most of the energy reflects away, therefore it's not very strong. And the corner normally has stronger reflection, so I think it's here. So then I made some distance calculations. This is 20 centimeters. I can measure it. Then this line is 29 centimeters. I can calculate it because it's 45 degrees downwards. And also I had the time measurement. So from that I can calculate the velocity. Now when I have the velocity, I can calculate the depth. I can calculate this line and also this line. And everything seems to confirm what we know about this vertical structure. Something more about this velocity from slanted beam measurement. So the beam is always about 45 degrees in the top layer, regardless of the permittivity. And then I can measure the distance, horizontal distance to the vertical structure, calculate the tilted distance, and the time is half of the measured time, so one-way time, and then I can get the velocity. And after doing that, I found that I had a small error in my paper. I just make a notification of this. Then some more measurements. Panning. The antenna box is kept tilted for the whole panning time at 60 degrees. So then the downward tilting is 45 degrees. And I was doing panning from -45 to 0 to 45 horizontally. And I got this. So I think it looks like it should. Then I made another measurement. It was old pelvis stone lining and 3 roots in the ground. So it was much more difficult than in the first place. And what I got in this time was something like this. In this case I was tilting up and down. Now I try to draw. I cannot draw, sorry, but I can show. So this edge of the stone lining, I think it's here, and tilting up and tilting down. The groundwater was at that time 40 centimeters below the ground. So when tilting up, I think it goes with something like this. And these two reflections, they are on top of each other, so it was not so good. Then the diameter of the well is about 80 centimeters inside. So I guess this is the reflection from it. So when tilting up and down, I'm not sure about this. Okay, some discussion. When the beam hits the target at a low angle, very little is reflected back. A wall may be invisible for the radar, so that seems to be a problem. Then one thing came into my mind. The helical screw blade of an auger might provide a good reflection when testing. I haven't tested that yet, but it's an idea I might do. And others are welcome to test more like this concept with their equipment. Then neoprene is not terribly expensive. This roller was about 100 euros. Conclusion: GPR tilting concept works. Gopher antenna beam is narrow, reveals vertical structures, and provides an additional method to estimate velocity. References actually. Okay. Some questions, and here's my email if you want to have some more information later. Okay, I'm done.
Thank you, Veli. Thank you very much for your presentation. Do we have any questions? We have a time for one short question. Matt, please.
Hello, thank you for your presentation. It was very interesting. Because you've got this narrow beam antenna, have you considered steering the beam rather than tilting the GPR antenna?
Yeah, that might be also possible. The antenna is quite large compared to the targets, so if I have beam steering, I need several antennas, and they could be much larger than the area of interest. So therefore, at least for now, I'm trying this beam tilting.
Brilliant, thank you.
Okay, Armin, just a short question, please.
Very short. Veli, the profiles you showed, are they continuous tilting or did you tilt in steps?
I was intending to do continuous tilting, but in practice, when I did it manually, it was in steps.
Okay, thank you.